Okay, so step one in this process is define our positions where we are going to predict the temperature, so define our nodes. There's different ways to do this. The most obvious way is you just uniformly distribute your n nodes along the computational domain. So my computational domain goes from x equals 0 here near the warm end down to x equals L near the cold end. I'm going to put nodes in that dimension, right? This is a one-dimensional problem, so I'm going to put nodes along that dimension x. I'll put node 1 right here at x equals 0, and then node 2 will be delta x away from that, and 3 and 4 all the way to node n, right? So I'm uniformly distributing these nodes. That gives me this equation here, right? It says that the axial location of node I is given by I minus 1 times L divided by n minus 1. So if I think about this, it should make sense. If I is equal to 1, so I'm talking about this node here, 1 minus 1 is 0, so I'm at x equals 0. Sure, that makes sense. If I is equal to n, so I'm this guy down here, then n minus 1 over n minus 1 is 1, so I'm at x equal L, right? So the distance between these nodes is the same for every node, and that distance is L divided by n minus 1. I've taken this length L and I've divided it up into n minus 1 little segments, right? This is probably not the best way to distribute nodes. The best way to distribute nodes is you put more nodes where things are happening, right? So you would put more nodes at places where the temperature distribution is doing something interesting, the temperature gradient is large. But this is a way to get started. All right, now I know where my nodes are. The next thing I have to do is a first law around a control volume, a first law on a control volume that's defined around each node. And I said that this is going to look a little differently if I'm talking about an internal node versus an external node, right? So an internal node is any node from I equal 2 down to n minus 1, right? It's a node where if I look up, I see another node. If I look down, I see a node, right? So that's an internal node. And I've drawn then a picture showing a control volume around that node. So here's my control volume. This control surface is supposed to split the distance between this node and this node, so right in the middle. Same thing here. For this problem where we're neglecting radiation and convection from the surface of the current lead, all that's going on is I have a rate of heat transfer in, through this surface, and then there's some generation of thermal energy inside of this node, right? So N is Q dot top plus N is Q dot bottom plus N is G dot has to equal 0. So that's my energy balance. And I guess this is a good time to make the point that it doesn't matter which direction I draw these arrows. Right, when I come into this spot right here and I say, I know there's energy crossing this boundary, I actually have no idea which direction it's going. I can draw this arrow as being in or being out, and it shouldn't affect the correctness of your final answer. Same thing for this guy here. But what's very important is that once I decided to draw my arrow going in, once I decided to make it an in, well, now I am stuck with that, right? I'm kind of married to that assumption now for the rest of the problem. So I've decided this is an in. So when I do my energy balance, which is in equals out plus stored, this is an in. It has to go on the left side. It's an in along with this thing, which is an in, along with G dot, which is an in, right? So these things are all ins. They add together to equal out plus stored. There's no outs and there's no storeds, so that side is 0. We know that one of these has to be an out, actually, right? And therefore, one of these will be negative, but that's okay, right? That'll happen. The other thing I have to keep in mind now in the next step is when I do my rate equation has to be consistent with the direction I've drawn these arrows as well, right? If I don't do that, I'll get into trouble. So that is the next step, which is, each of these terms I have to have a rate equation for. So let's think about this for a second. I wonder if I can get my pen. Sure. Okay, so top. Q dot top is driven by the temperature at this node minus the temperature at this node, right? That's consistent with the direction I do this arrow. And then the resistance of all this material that lies between those two temperatures, right? So it's going to be Ti minus 1 minus Ti, and this resistance is the resistance of all this stuff that lies between those two temperatures. So the resistance of this stuff, well, what is the resistance? It's the distance I have to transfer the energy, which is delta X, divided by K times the area that I have available for conduction, so AC, which is the cross-sectional area of this current lead. So this resistance is delta X over K AC. So this is my equation for Q dot top. Same thing for Q dot bottom, right? I've drawn it going this direction, therefore it must be driven by Ti plus 1 minus Ti, Ti plus 1 minus Ti, and then divided by the resistance of this material, which just happens to be the same thing. Okay, and then finally I have the generation of thermal energy not in the entire current lead, right? I'm not doing an energy balance on the entire current lead. I'm doing an energy balance on this little control volume right here. So it's the generation of thermal energy inside of this material that's enclosed in my energy balance. So that's going to be I squared times R, where R is the resistance, the electrical resistance of this material. So the electrical resistance of this material is the electrical resistivity times how far the current has to go, delta X divided by AC, right? So this is I squared times R. This is the rate at which energy is being generated due to ohmic dissipation inside of that control volume. So I just plug this guy into here, this guy into here, and this guy into here, and I end up with my equation. And actually, this isn't just one equation, this is a whole bunch of equations, right? This is an equation that I can write for every single internal node. So this is an equation that I can write from I equal 2 to I equal n minus 1. So there's n minus 2 equations. Unfortunately, I have n unknown temperatures, so I can't be done yet. And I have to go back and now separately look at the nodes that are lying right on the edges of my computational domain. And the reason is, again, these guys see something a little differently, right? If I look down from node 1, I do see a node 2, but if I look up, I don't see a node. I see the boundary conditions, right? I see the environment that is that my computational domain interfaces with, right? So this is where that comes into play. So here's my control volume. It goes around the material near node 1. You'll notice one thing is that it's half as big as the other ones, right? So I'm not going to take this control volume and extend it out into material that isn't part of my computational domain. My control volume stops at the edge of my computational domain, right? So it stops here at node 1, and then it travels halfway to node 2. So it's delta X over 2 long. In terms of an energy balance, I've decided again to draw everything as coming in. So Q dot top is in, Q dot bottom is in, and then G dot is in. So that's what I've done here. And then I have to do a rate equation for each of these guys, right? So Q dot bottom is no different than it was before. I have this thing being drawn as going from 2 to 1, so it'll be T2 minus T1. And then T2 and T1 are separated by the resistance of all this material here. Right, so let's see if I can make this work again. So it's the same amount of material that lies between T2 and T1. So this is going to be delta X over Ka. Q dot top. So Q dot top is driven by, well, let's see. Now I have this electrode at TH, and it's separated from this node T1 by this contact resistance, right? So it's going to be TH minus T1. Again, my temperature difference here is consistent with my arrow here. And then the contact resistance is the area-specific contact resistance divided by the area of that contact, right? So that's what I have for Q dot top. And then finally, I need G dot. So G dot, again, is I squared times the electrical resistance. The electrical resistance is how far do I got to move the current, is delta X over 2, delta X over 2 times the electrical resistivity divided by the cross-sectional area. So I just take this and put it into here, and this and put it into here, and that and put it into here, and I'm left with this equation that is the equation for the control volume defined around node 1, right? It's not a set of equations, it is just one equation. Obviously I have one more of these to do, which would be the one for node N. I guess I'm going to assume that you can derive that. It should look a lot like the one for node 1. And at this point then I have my n minus 2 equations for all of my internal nodes, and then I have one more equation for node 1 and one more equation for node n. So I have n equations and n unknowns, and they look like this, right? This is a complete equation set. It's not a differential equation. Instead, it's a set of algebraic equations, right? So I'm not ever going to have to solve a differential equation here. And there's different ways that we can try to solve these differential equations, right? This may be, depending on what n is, a pretty large set of differential equations, right? It's going to be maybe, if n's 100, it could be, algebraic equations. It could be 100 algebraic equations and 100 unknowns. It's pretty sparse, right? The three different ways we're going to talk about should pretty much cover you, I think. One is just throw them into ease. Ease solves equations. It's its job, so it does it pretty painlessly for you. Two is matrix decomposition. One thing you're going to find about ease is it's really not a program that is meant to solve huge systems of algebraic equations, right? It's not a numerical tool. Programs like MATLAB or compiled languages that are really fast are the place to go if you want to solve huge systems of algebraic equations. And there's two ways to solve those equations in programs like that. One is you put them into matrix form and you do some kind of matrix decomposition. And then two is you never put them into matrix form and you do something like Gauss-Seidel iteration, right? Both work pretty well. So let's go through these one at a time. We'll do the easy one today and then move into the harder ones next time. The easy one is you just put these into ease, right? So I'll take this set of equations right here and I'll literally just enter them into ease. I'm going to use arrays to do this because that's going to make my life easier. Let's see if I can open up ease here. So here's ease. This top part is just all the inputs. This is distributing my nodes. So I guess one thing you'll see is I have a duplicate loop here to do this, and I'm using arrays, right? So this equation right here that's inside of this duplicate loop is going to be duplicated for I equals 1 to n, right? That's what this means. So it's going to be literally what ease does when I compile or when I run is it takes this equation and it pastes it back into the equation window with I equal 1, and then it pastes it back in with I equal 2, and then it pastes it back in with I equal 3, and so on until it's finally done when it hits I equal n, right? That's literally what ease does, and then it tries to solve that set of equations. So this is just preventing you from having to do that, right? It's just a shorthand way for you having to do that. And the reason I'm saying that is that people sometimes forget that ease is an equation solver, right? So if I were to put something inside of this duplicate loop that I don't want duplicated, like a equal 1, right? That looks pretty reasonable, but it's actually a big mistake. And the reason is because every time ease goes through this duplicate loop, it's going to take this equation and it's going to plug in I equal 1 and put it in there. And then it's going to take this equation and say a equal 1. And then it's going to move on to I equal 2, take this equation, plug in I equal 2, throw it in there, and then it's going to put a equal 1 in there again. Well, now I have two equations that are a equal 1. I can't have two equations that are redundant, right? So you can see that because it's an equation solver, putting things inside of your duplicate loop that you don't actually want duplicated is going to be a problem, right? It's not like MATLAB or a formal programming language that uses assignments. If I was using assignments, this would be no problem. I would just sort of move through this. I'd make this assignment, I'd make this assignment, I'd make this assignment again, and I try to make this assignment again, and that'd be fine, right? This is kind of a stupid thing to do, to reassign A over and over again, but it wouldn't cause you an error, right? It would be fine. It's going to cause me an error if I do this in ease. All right, so now I have all my nodal positions, and I finally have to enter these equations right here, right? So let's see. This equation is for node 1. It's a single equation. That's this equation right here. Right? And again, you'll see I'm using arrays for the temperatures. This equation right here is for all of my internal nodes, so I'll put that in a duplicate loop from 2 to n minus 1. Right? So that's this equation right here. And then finally, this equation is for node n. It's a single equation, and it's right here. And if I didn't make a mistake, which I don't think I did, I should get a solution, right? So here is every nodal location right? Every element of my array is a node. This is the location of that node. This is the temperature that I predicted at that node, right? So I can now plot this, which I did here, and look at it and see if it makes sense. I think I'm pretty happy with that solution. Probably I should think about what I would really want to predict with this model, and if I'm trying to design a system, what I really probably care about most is what is the rate of heat transfer from the bottom of this current lead into my magnet, because that rate of heat transfer, unless I want my magnet to warm up, I have to remove that somewhere else with a cryo cooler or with some kind of boil off of some cryogen, and that's really sort of the pain of having a cryogenic system, is if I have a heat transfer into my system, I got to pull it back out again, right? So this heat transfer right here, I can calculate. It's just going to be Tn minus Tc divided by this contact resistance right here, right? So that's what I did somewhere. That's what I did right here, right? So this is calculating that rate of heat transfer to the cold end of my system.